Hey everyone, today we're going to talk about our physics project, the Gravitational Sandbox. So our group has created a model that allows users to play around with gravity. Simply click and drag around to shoot planets around, kind of like cosmic Angry Birds. The model will predict if the trajectory will result in a stable orbit indicated by its color. And you can also target out orbits and even the wall bouncing behavior to create amazing shapes too. You can play with the model over at this link, but we're first going to talk about some physics before we go into how we build it.
Okay, first let's talk about gravity. This is Newton's law of universal gravity. It states that for two objects with mass, there is a force between them. The equation looks like this and it follows the inverse square law. Also, note that this force is the same magnitude in both directions. This means that you pull on the earth just as much as the earth pulls on you.
Moving on, we'll see how gravity plays with circular motion. Let's say we have two bodies in circular motion, and one has an initial velocity. By Newton's first law, it should keep moving in a straight line because of inertia. But it doesn't. We've already established that it's moving in a circle, so the velocity changes direction and stays on the circle. This repeats, implying that there's an invisible force keeping it in a circle. That force is called centripetal force, and it's given by this equation here. So that means whenever there's circular motion, there's centripetal force, and vice versa. So we've talked about the force keeping it in a circle, but how fast are they moving? Let's look at circles first. We've established that centripetal force must be present for circular motion, but for planets, the only real force that exists is gravity. So these two must be equal to each other. After some derivation, we'll get this formula for orbital velocity. Next, let's look at ellipses. Actually, by Kepler's first law, each planet's orbit around the sun is not a circle, but actually an ellipse. But most of the time, they can still be approximated as circles. Also, observe how the velocity is one that is not constant, and it depends on the planet's position. We can break the orbital velocity down into its components, and I'll remove the orbit for clarity for now. We can censor our coordinate system on the planet and define the components as radial velocity and transverse velocity. You can see that as we reduce the radial velocity, the orbital velocity gets closer and closer to being the transverse velocity, and the ellipse becomes a circle.
Now, let's talk about planet's escape velocity. It is the velocity needed to escape something's pole. But before that, we need to look at energy. Specifically, kinetic and potential energy of something in orbit. Kinetic energy is the energy of something moving. This is its formula derivation, but we won't go too deep into that. Potential energy, however, is not as straightforward. We know that two objects have lower gravitational potential energy when they are closer together because less work is needed to pull them this far, and it will increase with separation. However, at infinite separation, the gravitational potential energy is defined to be zero, as they don't influence each other at such distances. So that implies that the gravitational potential energy must be negative for the second case, and very negative for when they're close, because gravitational potential energy increases with separation. Here's a diagram illustrating the situation, with gravitational potential energy defined to be at zero at the reference point. Again, here it's its derivation, but we won't get into it. With that, let's go back to escape velocity. When something escapes, its kinetic and potential energy becomes zero. Then we can use the conservation of energy to derive this relationship.
So after all that physics, it's time to dive into the code. The project was built using P5GS and HTML, and we're going to cover two main parts over here. So firstly, let's talk about how the particles interact with each other. So this is the code, and this is the function that runs whenever there's updating occurring. And so this is the more important part. Basically, what it does is that it finds the position the separation vector between the two particles and sets its magnitude equal to the gravitational force. After that, let's talk about how the code predicts orbits of particles. To make sure the orbits are circular, the velocity must be perpendicular to the circle and must have a suitable magnitude inside this range, so it doesn't escape and doesn't fall back into the sun. And so when a user clicks somewhere, we get its position vector, and when they release the mouse, we get that vector too. So for these two to be perpendicular, the dot product must be zero, and so this fact is reflected inside the code on the first line. We check if the dot product is zero and if the velocity is inside the range over here. But because computers aren't perfect, we introduce some small error bounds so that the user can click and drag more easily. So there are many applications of this project actually. It could be used as an educational tool, promoting hands-on virtual learning in line with SDG 4. It could also be used to make some amazing artworks. And so here are some mesmerizing examples that we've made. And all these examples and structures arise from the simple fact of gravity. And with that, that concludes our presentation. Thank you for watching.